Hello, everyone. A very warm welcome to my genetics class. The topic for today's discussion is pedigree analysis. Now, before we start our discussion, let's first know what is pedigree. Pedigree is a chart or a diagram, you can say, that shows the inheritance of a trait or healthy condition through generations of a family, right? So, here you see pedigrees are used to analyze the pattern of inheritance of a particular trait throughout a family. Pedigrees show the presence or absence of a trait as it relates to the relationship among parents, offsprings, and siblings. This shows the presence or absence of a trait within a family across generations. So, in simple words, what we can say is that if a disease is detected in a family, a pedigree helps us to understand whether this is already there in the family, from whom did the affected individual inherit this, and what are the chances of this individual to pass this trait to the next generations. This entire story is summarized in those diagrams which we are going to study. These diagrams will tell us everything about a particular trait and its inheritance and how we can actually avoid falling prey to it if we are little aware of the genetics of the disease, rather genetics of its inheritance pattern. Okay. Yes. Now let's now see, these are certain symbols which are commonly used in pedigree analysis. The the square here represents male, the circle female, the the shaded one, the shaded square and shaded circles represent affected individuals. This represents mating. See here, come here, see this line here, this horizontal line connecting the square and the circle. This line is showing mating between two people. Here you see this one, this box you follow, this green rectangle, you see children of the two people above. It shows the number of children this couple has. See here, come back here, see. What does this show? Offspring in birth order. 1 and 2 are generations. Offsprings numbered 2, 1 and 2, 2. This symbol is for identical twins and the symbol is for non-identical twins. You don't need to mug up these things actually. As you keep on practicing pedigree analysis, you will be familiar with these symbols and terms. Fine. Come, see. Pedigree can be analyzed to determine the mode of transmission for a genetic disorder or disease. Okay. First is dominant, second is linkage. Whether the disease alleles are dominant or recessive This is one parameter actually. Whether it is dominant or recessive, we'll get to know this, and then linkage. What is that? Whether the disease alleles are X-linked or autosomal. That means they are on the sex chromosome or they are autosome related. They are in the autosomes. Okay. Now here we are going to discuss about these autosomal dominant trait, autosomal recessive trait, X-linked dominant trait, and X-linked recessive trait. I will take each one of these separately. This is a diagram for autosomal dominant trait. What happens here? See. Here, see, the trait should not skip generation. That means what? If the if the disease is there, it will not skip generations. All right? This means what? The trait is common in pedigree and is found in every generations. See here, when an affected person mates with an unaffected person, this one, see, when an affected person mates with an unaffected person, unaffected means the circle is not shaded. Approximately 50% of their offspring should be affected. Here you see, what are the two offspring? This one and this one. 50% affected. See here, two offsprings are here. Two offspring. Out of the two, one is affected. This means what? 50% affected. Indicating also that the affected individual is heterozygous. Correct? This shows, concentrate here, this shows one individual is unaffected. This person is unaffected and this person is affected. They produce two children. One of them is affected, that is 50% is affected and 50% is not affected. The trait should appear in almost equal numbers among the sexes. Next point. See, it's not that only the males are affected or the females are affected. You can see equal numbers. Both traits are, both sexes are affected. That is, both males and females are affected. And always remember here for autosomal dominant one, unaffected carriers are not found. Hmm. Unaffected carriers are not found here. Remember this. The affected individual here transmits the trait to half of their children. Okay. Affected parents can have unaffected children. Remember, affected parents can have unaffected children. Here only you can see, affected parent, unaffected children. Okay. The trait should appear in almost equal number. Here also it is satisfying. See, both the sexes are affected. And remember, the affected individual should have at least one affected parent. One affected parent is a must. Clear? So these are the three most important criteria for autosomal dominant trait. And you see, uh, when this person, this unaffected person, marries an unaffected person here, this unaffected female marries an unaffected male, none of their children gets affected. Here you see both parents are affected, father as well as mother. Majority of their offsprings are affected here. One is unaffected. What did I say? Unaffected carriers are not possible. Unaffected children here is definitely a recessive one. Unaffected one is a recessive one. If it has a dominant factor, it will definitely show up the disease. In both these conditions, whether it is capital A or capital A small a, both gives the disease since it is dominant. Got it? Unaffected carriers are not possible here. Clear? Some important examples of autosomal dominant traits, autosomal dominant diseases, Huntington's disease, then Marfan syndrome. Another important one is brachydactyly. Then you must have heard of familial hypercholesterolemia. That is also an autosomal dominant trait. Okay. Next, we talk about autosomal recessive trait. See, here what happens? Here also you will see both males and females are affected. Both the sexes affected. Both males and females affected. Like the autosomal dominant one. Here you see, first thing, the trait often skips generation. Fine. It often skips generation, but if both the parents are affected, it will not skip generation. If both the parents are affected, it will not skip generation. I'll use two different colors to show you this. See here. Here one parent is affected. This part you just concentrate on. This blue box. One parent is affected, one is unaffected. Here you can see none of the children got the disease. It has skipped generation. Generation skipped. Though the father is affected, none of the children got affected here. Fine. So this condition, this box, this condition is matching with this. Trait often skips generation. But what did I say? One more thing, if you have heard, I have just said that it will not skip generation if both the parents are affected. Look at this red. Here, both the parents are affected. Did it skip generations? Yes or no? It did not skip generation. Both the children got affected. Okay, it will not skip generation if both the parents are affected. Remember this. Next point, see, almost equal number of affected males and females. This is the point with which we had started our discussion. This is the point with which we have started our discussion. See, both males and females are affected. Fine. Next is traits are often found in pedigrees with consanguineous matings. What is consanguineous mating? Who can say what is consanguineous mating? Consanguineous matings or marriages are those between related individuals. Okay. They like defined simply as those that share a common ancestor. Understood? If both parents are affected, if both parents are affected, all children should be affected. This one. If both parents are affected, all children should be affected. Examples are cystic fibrosis, important examples, sickle cell anemia, Tay-Sachs disease. Fine. Then another few examples are also the alkaptonuria. That's also an important one. Let me write. Alkaptonuria, then lysosomal storage disease, all these things are also there. Wilson disease. Hmm, clear? Next, we'll come to X-linked dominant trait. Fine. Yes, this is a very important one. X-linked dominant trait. What do we see here? See, what does it say? Trait does not skip generation. Dominant again. So how will it skip the generation? Fine. See, in every generation you will see one shaded thing. Affected, affected. So in every generation you see affected individuals are present. So the trait does not skip generation. What happens here? Affected males must come from affected mothers. Why do you think this? Affected males must come from affected mothers? Because females have what? XX, males have XY. Yes, right? Now what happens here? The affected males inherit the trait from affected mothers. How is this happening? Father don't give X to the son, right? Remember this. This is important. See, fathers, they don't give X to the son. Instead, what do they give? They give Y to the son. Mothers, they give X to the son. Therefore, if the problem is with the X and if the son is having the X, then common sense, from where did it come? It has come from the mother and not from the father. Correct? Approximately half the children of an affected heterozygous females are affected. Okay, see, what does it say? Approximately half the children, suppose 4 children are there, 2, like that. Half the children of an affected heterozygous female are affected. If the female is heterozygous, 50% of her children will be affected. Affected females come from affected mothers or fathers. Correct? Since it is in the X chromosome, hmm, for females, for daughters, they can inherit it from mother as well as father. Because see, for daughters, father is also giving one X to the daughter, mother is also giving one X to the daughter. If the problem is with the X, the daughter can inherit that X, that diseased X, from either father or mother, anyone, right? Now, last one, all the daughters of an affected father are affected. Remember this. None of the sons are affected. This is a very important line. None of the sons are affected. All the daughters of an affected father are affected. Why, see? Why is it like this? Father has XY, and this problem is with the X only. Daughter has XX. This one X is coming from the mother, the other X is coming from the father. Father cannot give Y to the daughter. It has to give X only to the daughter, and this X is only the problematic one. So it will come from the father. No matter what, it will come from the father. So all daughters of an affected father are affected. So if the affected father gives birth to a daughter, then for sure the daughter is going to get affected. That means the daughter will be a diseased one. Okay. Examples are what? Akari syndrome, Fragile X syndrome. hmm, then some Rett syndrome. Rett syndrome is also there. Vitamin D resistant, ricket. All these are prominent examples of this X-linked dominant trait. The last one we'll talk about is what? X-linked recessive trait. This is also an interesting one. You see, most affected individuals are male. Majority are males here. Hmm. Most affected individuals are males. That means what? Females are generally carriers here. Females are, I'm not telling females are never affected. They are sometimes. But generally they are carriers. And it's a rare trait. A trait that skips generation. Hmm. X-linked one, remember, it's a rare trait and skips generation. It's a rare trait and it skips generation. Okay. What happens here? See, the affected male result from affected mothers. Why? Because mothers will mothers have nothing else other than X to give to her sons or daughters, whatever. Hmm. So it will definitely give that affected X to the son. So affected males result from affected mothers or carrier mothers because they have affected brothers, fathers, or maternal uncles. Fine. Now, affected females come from affected fathers or affected or carrier mothers. Now, females have got the option of getting X from mother as well as father. So, the daughter can inherit this trait or this disease or this problem from the mother or the father. The father has no other option than to give the affected X to the daughter. And the mother, if even if she is a carrier or she is an affected individual, both in both the conditions, she has the potential to give the X, affected X to the, or the disease carrying X, trait carrying chromosome to the daughter. Okay. The sons of affected females should be affected. Very, very important. If the mother is affected, there is no chance for the son to escape. Last one. And why there is no chance? Because the mother has no other option than to give that affected X to the son. Mother has only X, both the X. There is no other chromosomes like the father. The father has X as well as Y, but the mother has got no options, right? So if the son is affected, he has definitely inherited that X from the mother. I mean, the sons of the affected females should be affected if you take the reverse way. Now, the last point, approximately half the sons of the carrier females should be affected. If the female is a carrier, then chances are that 50% of her sons will be affected. Fine. Now, see this. In this condition, see this block, this part only, this part. If here you see both are unaffected, definitely here the mother is a carrier. Otherwise, how did she pass the eggs to this son? The son got affected here. That means what? This female was definitely a carrier. Here you see both the parents are affected, all children affected. No chance of escaping. Try to follow this comments and try to match it with the diagram. Otherwise, you will never understand. And once this concept gets clear, whatever pedigree charts you are being given, you will be able to deduce it. You'll be able to solve it out. Okay. Now coming to the examples, Duchenne muscular dystrophy, some types of color blindness and hemophilia are some of the very popular examples of X-linked recessive pedigree. So here we come to an end of our lecture. I hope you have enjoyed learning pedigree analysis with me. If you have any confusion, any doubt of any kind of questions if you have in your mind, please feel free to get back to me in the comment section. Till then, stay tuned and happy learning. Bye bye.